Hello. In our last lesson, we looked at how to graph polar equations and how to convert back and forth between the polar coordinate system and the rectangular or Cartesian coordinate system. So today we're going to look at how to find the slope of a polar curve at a specific point, and then also how to write the equation of a tangent line to a polar curve at a specific point. And we're going to think about this in a similar way as we did when we were working with parametric equations. When we talk about the slope of our polar curve, we're really referring to the slope in that Cartesian or rectangular coordinate system. So we do want to find dy over dx. The problem is our equation in polar form is not written in terms of y and x, it's written in terms of r and theta. So we need to find a way to express dy dx in terms of theta. We know that our polar equations are generally written in the form r equals f of theta. And this notation here, r equals f of theta, is just telling us that r is a function of theta. So most of the time our equation can be solved for r, where you have r equals on the left, and then only terms involving theta on the right. So if we want to find dy dx, we can accomplish that by finding dy d theta divided by dx d theta. And we saw this same thing happen when we were working with parametric equations. Oftentimes in parametric equations, the parameter is called t, so we could say dy dx equals dy dt over dx dt. But even in parametric form, we saw that the parameter could be called theta, so we worked with equations like dy d theta over dx d theta. So to find dy dx, we want to find dy d theta and dx d theta. But how do we find dy d theta from an equation in the form of r equals f of theta? For example, our equation might be r equals 2 sine theta. How would we get dy d theta from that? Or what if our equation was r equals 3 theta? How would we get dy d theta from that? So we're going to go back to our conversion formulas where we can try and manipulate a polar equation to get it in rectangular form. Now we're not going to go all the way to converting our polar equations to rectangular form, although that is an option. If you can rewrite your polar equation in rectangular form, then just calculate dy dx. But we're going to see that we can still find dy d theta and dx d theta even without converting our equation into rectangular form, knowing that we had these conversion formulas, x equals r cosine theta and y equals r sine theta. R right here is our polar equation in that form r equals f of theta. So for example, if our polar equation was r equals 2 sine theta, then I could just substitute that in for the r in this conversion formula, and then multiply by cosine theta, and there I have an equation for x written in terms of theta. And if I have an equation for x written in terms of theta, I can find dx d theta just by taking the derivative with respect to theta. Similarly, we can write the equation y equals r sine theta strictly in terms of theta by substituting something in for r. Whatever r is equal to, that f of theta, we'll substitute here in for the r. So dy d theta would be the derivative of this function right here, f of theta sine theta prime. And even though I'm using this kind of simplified notation with just the prime, I do mean with respect to theta. And then our dx d theta is just the derivative of this guy right here, which is a function of theta. So f of theta cosine theta prime. Now to find these derivatives, we are just going to take the derivative with respect to theta. And in the numerator, so the f of theta is just general at this point. We're not talking about a specific polar equation. We're keeping this very general so that we can develop some type of formula here. But to take the derivative of my numerator, I'm going to have to use the product rule. So derivative of the first times the second plus the first times the derivative of the second. And to find the derivative of the denominator, I'm also going to use product rule. Derivative of the first times the second plus the first times the derivative of the second. And that is my dy dx. So it looks pretty complicated, but when we have an actual equation to work with, it's really not so bad. And now we can use this equation for dy dx. This is what dy dx is equal to. And we can use that to find the slope of our polar curve at a specific point. We can use it to find the slope of the tangent line to the curve at a specific point. So let's just make a note that we can use this, use dy dx to find the slope of the line tangent to our polar function, which is r equals f of theta, at the point r comma theta. So we see our dy dx equation at the top, and keep in mind here that this is equal to dy d theta over dx d theta. And this is giving us the slope of the tangent line to the curve. So when is it that we have a horizontal tangent line, and when is it that we have a vertical tangent line? Again, this is very similar to what we looked at with parametric equations. And even going back a lot farther than parametric equations, in general, when is it that you have a horizontal tangent line? If your derivative is in fraction form. We have a horizontal tangent line if the derivative is equal to 0, meaning the numerator is 0 and the denominator is not 0. So we want to see 0 over not 0. Don't use that notation, that's not proper notation. But we could say 0 over k, for example, where k is not 0, but k is some real number. So if you end up in this situation, your tangent line is horizontal. The slope is going to equal 0. And we saw that was true with parametric equations as well. When do we get vertical tangent lines? Well, that happens when the numerator is not 0 and the denominator is 0. So when we get something in the form of k over 0, again where k is not 0, but it is some real number. In this case, we're going to have a vertical tangent line. Now, if dy d theta is equal to 0 and dx d theta is equal to 0 for a particular value of theta, then we really can't make a conclusion. This is going to be inconclusive. It could be that there's a cusp there, or just something else unusual going on the graph, or not even. So we would just have to use some other technique to analyze what's happening on the graph at that point if both of these derivatives are 0 simultaneously. Let's take a look at a specific example. Find the points of horizontal and vertical tangency for the polar curve r equals sine theta. And we're only going to work on the interval from 0 to pi, theta between 0 and pi. Let's start with horizontal tangent first. When is it that we're going to have a point of horizontal tangency? Well, we know in order for that to happen, our slope dy dx is going to have to equal 0. And in order for that to be true, we need dy d theta to equal 0 and dx d theta to not equal 0. In order to find dy d theta and dx d theta, we're going to have to write expressions that are equal to x and equal to y. So we need to use that conversion formula to say x equals r cosine theta. And then here, we know what r is. R is sine theta, so we're going to substitute that in for the r. So x is equal to sine theta cosine theta. And now that I have x defined in terms of theta, I can find dx d theta. So the same thing for finding dy d theta. We first have to express y in terms of theta. We know that y equals r times the sine of theta. And so we're going to substitute sine theta in for the r here, and we get y equals sine theta times sine theta, or sine squared theta. And now I can find dy d theta. So let's organize our work here. X is equal to sine theta cosine theta for this particular polar curve, and y is equal to sine squared theta. Now we want to find the derivative of x and the derivative of y with respect to theta. Because I'm going to be taking the derivative, I'm going to rewrite sine squared theta as the sine of theta squared, just to make it easier to see that how I'm going to use the chain rule there. So for dy d theta, start with the y, not with the x. For dy d theta, we're going to have 2 times the sine of theta times the derivative of the sine of theta. Okay, so I use chain rule there. I have over here, I've got stuff squared, and the derivative of stuff squared is 2 times stuff to the power 1 times the derivative of the stuff prime. Okay, so we end up with 2 sine theta cosine theta. Then for dx d theta, we're taking the derivative of x here, and I have a couple of options. I can go ahead and take the derivative of this as is using product rule, or I could use a trig identity to rewrite this so that I wouldn't have to use the product rule. The choice is yours. I don't know which way seems easier for you, but I do know that sine theta cosine theta is equal to 1/2 sine 2 theta. So if I write x as 1/2 sine 2 theta, I don't have to use the product rule, but I do have to use the chain rule. Then the derivative here would be 1/2 is a constant multiple, so I'll hold that in my mind. The derivative of sine of stuff is cosine of stuff times the derivative of the stuff, so times 2, but then times the 1/2 constant multiple, and the 1/2 times 2 is just 1. Now for the points of horizontal tangency, I need to know when dy d theta equals 0 and dx d theta is not 0. So let's solve dy d theta equals 0. dy d theta will equal 0 when 2 sine theta cosine theta equals 0. And then using the zero product property, we would set each factor equal to 0. So this will be true whenever sine x equals 0 and whenever cosine x equals 0. Or cosine theta, rather. Sine theta equals 0. Well, where does sine of an angle equal 0? That's going to happen at 0 and pi and 2 pi and 3 pi. And negative pi and negative 2 pi and so on. But remember, we are working on a restricted domain. Our theta values can only be between 0 and pi, not including pi, but including 0. So here we get theta equals 0. The next solution bigger than that would be theta equals pi, but we're not allowed to use pi. So moving on, where does cosine theta equal 0? That's when theta equals pi over 2. And then 3 pi over 2, but 3 pi over 2 is outside of our interval. It's bigger than pi, so I won't use that. Now let's go ahead and solve dx d theta equals 0. So that will be true when cosine of 2 theta equals 0. And the cosine of an angle equals 0 when the angle, and here the angle is not theta, the angle is 2 theta. So whenever the angle is equal to pi over 2, 3 pi over 2, and I could keep going, but I know I'm only going to have 2 solutions at most. But if you're not sure, about that, we can just keep listing a few more. We could even write all of the solutions by doing something like plus 2 pi k, or plus pi k in this case. But the next one would be 5 pi over 2, and so on. And of course, we also have some solutions prior to pi over 2, but remember, our domain starts at 0. So now to solve for theta, I would divide everything by 2, and that would give me pi over 4, 3 pi over 4, which is still less than pi, so I can use that one. 5 pi over 4, however, is bigger than pi, so I'm not going to use that one. And I knew I was only looking for 2 solutions there anyway. Now, do we have any common solutions? Are there any values of theta for which dy d theta and dx d theta are both equal to 0? And in this case, no, there are not. So that makes this problem a little bit easier. We can go ahead and write out our solution. We know we have points of horizontal tangency when theta equals 0 and theta equals pi over 2. Now the question is asking us for the points, so we have a little more work to do. Find the points, we have to give the coordinates, we have the theta values, but to write the coordinates of the points in polar form, we also need to have the corresponding r values. So when theta is 0, what does r equal in the original polar equation? We're going to go back to that original polar equation here and find our coordinates. So when theta is 0, r equals the sine of 0, which equals 0, giving us the point 0, 0. When theta equals pi over 2, coming back over here, r equals the sine of pi over 2. And we know the sine of pi over 2 equals 1. So r equals 1. So we have r, comma, theta. Those are the points of horizontal tangency. And then points of vertical tangency, those are all of the points where dx d theta equals 0 and dy d theta is not. So we have 2 points, one where theta equals pi over 4. So we'll go back to the original equation. When theta equals pi over 4, r equals the sine of pi over 4, and the sine of pi over 4 is 1 over root 2. You can also write that as root 2 over 2 if you prefer. And then when theta equals 3 pi over 4, we have r equals the sine of 3 pi over 4, and the sine of 3 pi over 4, that is quadrant 2, that is also 1 over root 2, or root 2 over 2 if you prefer. Those are the points of vertical tangency. So once again, points of horizontal tangency occur at 0, 0 and at 1 pi over 2. And let's locate those points on the graph. 0, 0 would be this point right here, and it does in fact look like we have a horizontal tangent right there. 1 comma pi over 2, so the angle is pi over 2, and the r value is 1, and that takes us to this point right here, which again definitely looks like we have a horizontal tangent there. Our points of vertical tangency were 1 over root 2, comma, pi over 4, and 1 over root 2, 3 pi over 4. And graphing those points, so pi over 4 makes a 45 degree angle here. So there's the pi over 4. And we can go ahead and do 3 pi over 4 as well. 45 degree angle in quadrant 2. There's 3 pi over 4. And this point right here and this point right here would be on the curve at those theta values. And we can see that we do have vertical tangent lines at each one of those points. Let's look at another example. Find the points of horizontal and vertical tangency for r equals 2 times 1 minus cosine theta. So you might want to pause the video here and see if you can do this example on your own. We'll start by writing x equals r cosine theta. So that becomes x equals the r, I'm substituting in this right here. So 2 times 1 minus cosine theta, and then for r sine theta, it's 2 times 1 minus cosine theta, sine theta. Now I need to find dy d theta and then dx d theta. For dy d theta, I'm going to use the product rule. And when I use the product rule here, I'm going to group the 2 times 1 minus cosine theta as one factor, and then the sine theta as my second factor. So derivative of the first, 2 is a constant multiple, so 2 times the derivative of 1 minus cosine theta is sine theta. So that's the derivative of the first factor times the second factor, which is another sine theta. So I could simply say 2 sine squared theta. Okay, that's the first part of the product rule. And then plus the first factor, 2 times 1 minus cosine theta, times the derivative of the second factor. All right, there's my dy d theta. My dx d theta, I am also using product rule, so I will group this as the first factor and then just the cosine theta as the second factor there. So derivative of the first, 2 times sine theta, times the second, plus the first, times the derivative of the second, which is negative sine theta. We may want to simplify this a bit. I can distribute the cosine theta here and distribute the 2 at the same time. So the first term won't change, 2 sine squared theta. But then we have 2 cosine theta plus 2 cosine theta. And then minus cosine squared theta times 2. So minus 2 cosine squared theta. On the bottom, I can distribute the sine theta and then also distribute the negative 2. So first term, 2 sine theta cosine theta. And then we'll have sine theta times negative 2. And plus 2 sine theta cosine theta. Did I do that right? Sine, cosine, negative, negative, then 2. Yes, so if I add another 2 sine theta cosine theta, I can add it to the 2 sine cosine theta that I already have, because those are like terms, and that becomes 4 sine theta cosine theta. All right, now we get to set the numerator and denominator each equal to 0 and solve. For dy d theta, that's the numerator, we're setting it equal to 0 and solving. So 2 sine squared theta plus 2 cosine theta minus 2 cosine squared theta equals 0. I want to rewrite this all in terms of cosine. So I can use a trig identity here. Sine squared theta is equal to 1 minus cosine squared theta. And then I would distribute that too. So that's going to give me 2 minus 2 cosine squared theta plus 2 cosine theta minus 2 cosine squared theta equals 0. And these are like terms here. So 2 minus 4 cosine squared theta plus 2 cosine theta equals 0. This is a disguised quadratic. So I'm thinking about this like w equals cosine theta, and then I can rewrite this as 2 minus 4w squared plus 2w equals 0, which would be equivalent to 4w squared minus 2w minus 2 equals 0, and hopefully that is factorable. Well, right away I can divide everything by 2, so let's try that. 2w squared minus w minus 1 equals 0. And let's see if we can factor that. So 1 and 1, we need to get a negative w in the middle, so negative positive. Let me multiply that out quickly to check. 2w squared minus w minus 1. That looks correct. And then we would set each factor equal to 0 to continue solving. So keeping in mind that w equals cosine theta, that means 2 cosine theta plus 1 equals 0, or w minus 1 equals 0. So cosine theta equals negative 1/2. Oh, I should have put the cosine in there. Or cosine theta equals 1. Okay, these are easy unit circle angles. So the cosine is negative 1/2 in quadrants 2 and 3. Reference angle 60 degrees, or pi over 3. So that's going to be pi minus pi over 3 and pi plus pi over 3. So theta equals pi minus pi over 3 is 2 pi over 3. And then pi plus pi over 3 is 4 pi over 3. And do we have we don't have a restricted domain here, so actually there are infinitely many solutions here. So we need to tack on a plus 2 pi k here, plus 2 pi k for any integer k. And then cosine theta equals 1 when theta equals 0 or 2 pi or 4 pi or 6 pi, etc. So we will add on 2 pi k here as well. All right, and let's see where dx d theta equals 0. So dx d theta equals 0 when 4 sine theta cosine theta minus 2 sine theta equals 0. I can factor out 2 sine theta, leaving behind 2 cosine theta minus 1. Using zero product property, this gives us sine theta equals 0, or 2 cosine theta minus 1 equals 0. So cosine theta equals 1/2. Sine of theta equals 0 at 0 and pi and 2 pi and 3 pi, etc. So at 0 plus multiples of pi. And then over here, cosine is theta is equal to 1/2 at 60 degrees, or pi over 3 in quadrant 1. So theta equals pi over 3. That's quadrant 1, and plus 2 pi k. Or also quadrant 4, we would have theta equals, so quadrant 4, it would be 2 pi minus pi over 3. So 5 pi over 3 plus 2 pi k. So do we have any common solutions here? I think we do. 2 pi over 3 is only a solution for dy d theta equals 0, not for dx d theta equals 0. And if we add multiples of 2 pi to that or subtract multiples of 2 pi, we're still not going to have a common solution with dx d theta equals 0. Okay, same with 4 pi over 3, that one's good to go. But theta equals 0, this one is problematic because theta equals 0 is also a solution over here. Now we have to be careful though in just like crossing that out entirely, because we need to omit the 0 and 2 pi and 4 pi and so on, negative 2 pi and so on. But over here, it's 0 plus pi k. So this is 0 and pi and 2 pi and so on, and negative pi, and so on. So we're really only omitting the even multiples of pi, but keeping the odd multiples of pi over there. Okay, so we can keep the odd multiples of pi, and then our pi over 3 solution is good. 5 pi over 3, that solution is good as well. So points of horizontal tangency are going to occur when theta equals 2 pi over 3 plus multiples of 2 pi, and 4 pi over 3 plus multiples of 2 pi. We're going to throw out the solutions that were just multiples of 2 pi. Okay, and we'll just say up here, k is any integer. Now we're asked for points of horizontal tangency, and points means coordinates of those points. So we would substitute our theta values into our equation for r. The cosine of 2 pi over 3 is going to give me the same answer as the cosine of 2 pi over 3 plus any multiple of 2 pi. So this, even though like technically we should add 2 pi k to list all of the solutions, they're just going to be repeats of that original point, right? Just means we're just rotating another 360 degrees or another 2 pi along the graph, and then we're going to land in the same spot again. So we really only just need to find one point from this first set of solutions and then one point on the curve for the next set of solutions. Now to find the points of horizontal tangency, let's find the r value that corresponds to an angle of 2 pi over 3. So when theta is 2 pi over 3, the cosine of 2 pi over 3 is negative 1/2. 1 minus negative 1/2 is 3/2. 3/2 times 2 is 3. So we have r equals 3. And 4 pi over 3, cosine of 4 pi over 3 is also negative 1/2. Subtract that from 1, multiply by 2, we also get r equals 3. So our points, if we write them in the form of r comma theta, would be 3, 2 pi over 3, and then 3, 4 pi over 3. And let's plot those points. So 2 pi over 3, that is 120 degrees. So that's right. And I can tell I'm off a bit because I know r is supposed to be 3. So it would have made more sense to start with the r value for plotting that point rather than starting with the angle. R value of 3 is that point right there. Okay, so there's our angle 2 pi over 3. And then if we follow along a radius of 3, we also have this point right here where r equals 3, and that is our other angle, 4 pi over 3. And it does in fact look like the tangent line at those points would be horizontal. So that's good. Now just looking at the graph here, I can see that I should be finding 3 points where the tangent line is vertical. We should have 3 solutions here. So let's go back to our solutions and see if we did that correctly. For our points of vertical tangency, when we solved, we found theta values of, now we threw out the 0, 2 pi, 4 pi, etc., but we kept the odd multiples of pi. So theta equals pi, and then 3 pi and 5 pi and so on. So pi plus 2k pi, or 2 pi k. And then we had pi over 3 and also 5 pi over 3. But again, with this, adding the multiples of 2 pi is just going to take us back around to the same point. So we really only have to get coordinates for pi, pi over 3, and 5 pi over 3. And we will substitute those theta values back into the polar curve, the original curve. And let's see, the cosine of pi is negative 1, so it's 1 minus negative 1 is 2 times 2 is 4, giving us 4 comma pi. 4 comma pi, go to an angle of pi and a radius of 4, that's this point right here. So we've got that one. And then at pi over 3, cosine of pi over 3 is 1/2. 1 minus 1/2 is 1/2 times 2 is 1. So 1 comma pi over 3. Okay, where do we have a radius of 1? So that's this point right here, and that does in fact look like pi over 3. Pi over 3, and we have a vertical tangent there. So that worked out well. And then 5 pi over 3, the cosine of 5 pi over 3 is also equal to 1/2, so we're going to get r equals 1 again. So 1 and 5 pi over 3, and that would be this point right here where r equals 1, and here's our angle 5 pi over 3. And we've got our vertical tangent line there. Now let's take a look at tangent lines at the pole. When we refer to a tangent line at the pole, we're saying that the point of tangency is the pole. And if you remember, the pole has coordinates 0, 0. In the Cartesian coordinate system, the origin, right, has coordinates 0, 0, x, y. But in the polar system, it also has coordinates 0, 0. But there are lots of different ways to express the coordinates of the pole. So it's also possible that the coordinates could be 0, pi over 2, or 0, 3 pi over 7. Any value of theta that produces an r value of 0 is going to take us to the pole. So as we are talking about tangent lines at the pole, you're going to see some different notations here. You're going to see theta, and you're going to see an alpha, and they both represent angles. So let's just talk about the difference for a moment. The theta is just the variable in the equation. It just represents an arbitrary angle on our polar curve. Whereas the alpha is going to be a very specific angle. It's going to be an angle such that when you substitute that value in for theta, you get 0. So to find a tangent line at the pole, we want to keep in mind that if r equals f of theta passes through the pole when theta equals alpha, then f of alpha equals 0, right? We have in general our equation r equals f of theta, and to figure out where it passes through the pole, we want to know where the r value is 0. So then the equation becomes 0 equals f of theta. And when we solve for theta, we're going to get specific values of theta, and those specific values of theta we're calling alpha, okay? So that means that f of alpha equals 0. So now let's look at our slope equation, our dy dx equation, and we developed this earlier in the lesson. Dy dx equals f prime of theta sine theta plus f of theta cosine theta over f prime of theta cosine theta minus f of theta sine theta. If we're talking about a tangent line at the pole, it turns out that the slope of that tangent line at the pole simplifies to just tangent of theta. So let's see how that happens. If our point of tangency is the pole, then we have f of theta equal to 0. So if f of theta is equal to 0, then this part of the equation becomes 0 times the cosine of theta. 0 times the cosine of theta is 0. So this drops out of the equation. And in the denominator, something similar is going to happen. If f of theta equals 0, then 0 times sine of theta equals 0. So this drops out of the equation. Okay, that's all gone. Now, what about what we have left? We have f prime of theta sine theta divided by f prime of theta cosine theta. And as long as f prime of theta isn't 0, we can just cancel these out, and we will end up with sine theta over cosine theta, or just tan theta. So we have this simplified version of our slope equation, but remember, this is only going to apply to tangent lines that pass through the pole. And we want to be careful here in noting that f prime of alpha cannot equal 0. What would happen if f of alpha were equal to 0 and f prime of alpha were equal to 0? So if we rewrote our dy dx equation here, substituting alpha in for the theta, we know this would be 0 times cosine of alpha, and this would be 0 times the sine of alpha. So this whole term would just be 0, and this whole term would just be 0. And if f prime of alpha were 0, then here we would have 0 times sine alpha over 0 times cosine of alpha. And 0 times sine alpha is 0, and 0 times cosine alpha is 0. So we would end up with 0 over 0. But 0 over 0 is an indeterminate form. So we don't want to end up in that situation. So when we're looking for tangent lines at the pole, we want to make sure that when we find our alpha values, that they don't make the derivative equal to 0. So to find the tangent lines at the pole, we're just going to start by finding these alpha values. So set your polar equation equal to 0 and solve for theta. Those solutions is what you're seeing here called alpha. Then we want to verify that the derivative at alpha is not 0. And as long as that's true, we have our tangent lines at the pole. Let's look at an actual example. Find the tangent lines at the pole for this rose curve, r equals 2 cosine 3 theta. So we start by figuring out where does r equal 0. Let r equal 0 and solve for theta. I can divide both sides by 2. I have 0 equals the cosine of 3 theta. And here I can use my unit circle knowledge to help me. Where does the cosine of an angle equal 0? The cosine of an angle is 0 at pi over 2 and 3 pi over 2. And then multiples of 2 pi added or subtracted to those solutions. But our angle here, be careful, our angle here is not theta. Our angle is actually 3 theta. So we have 3 theta equals pi over 2, 3 pi over 2, and so on. Now I actually do need to list more than just these two, because 3 theta is changing the period of my cosine function. So I'm expecting, instead of just 2 solutions, 6 solutions. So I'm going to list out 6 solutions here, and some of them may end up being repeat solutions, which is okay, and we can ignore them. So pi over 2, 3 pi over 2. The next one would be 5 pi over 2. And then 7 pi over 2. And then 9 pi over 2. And so on. And of course, we can also subtract pi from these angles and get even more solutions. But I'm going to divide both sides by 3. So theta equals pi over 6. And then 3 pi over 6, which reduces to pi over 2. 5 pi over 6. 7 pi over 6. But 7 pi over 6 is actually a repeat of pi over 6. And let's see how that works. If I start graphing these solutions, theta equals pi over 6, 30 degrees. That's going to be this line right here. When you graph the polar equation, theta equals pi over 6, you get that line right there. When you go to graph theta equals 7 pi over 6, well, here's 7 pi over 6. So it's the same graph, and that's what I mean by it's a repeat solution. So I don't need to include that. And all of the rest of them are going to be repeat solutions as well. So we have pi over 2 as another one right here, pi over 2. And then 5 pi over 6. 5 pi over 6 would be over here. So I don't have enough space to label the 5 pi over 6 on the left side of the graph, but I can come over here and label this as negative pi over 6, or even 11 pi over 6. Now we want to make sure that f prime of theta does not equal 0 at these 3 values of theta that we have here. So there's a couple ways we can do that. We can substitute each one of these angles into the derivative equation, or we can just find the derivative, set it equal to 0, and solve and make sure we don't have any overlapping solutions. So f prime of theta, that's the same as r prime of theta, would just be, we have to take the derivative of this equation right here with respect to theta, dr d theta. Cosine of stuff, we have to use chain rule here. The derivative of cosine stuff is negative sine stuff times the derivative of the stuff times the constant multiple that was already there. So negative 6 sine 3 theta. When does that equal 0? We can divide both sides by negative 6. Sine of 3 theta equals 0. And then we can solve this equation. Again, the angle here is 3 theta, not theta. So sine of an angle is equal to 0 when the angle is 0 or pi or 2 pi or 3 pi, etc. So all multiples of pi. So we have 3 theta equals 0, pi, 2 pi, and so on. I could also write this as 3 theta equals 0 plus pi k if I wanted to do that. So I can work with either one of these forms right here. And divide both sides of the equation by 3, we get theta equals 0 plus pi over 3k. Or if I'm working from the top equation and I want to list out some solutions, theta equals 0, pi over 3, 2 pi over 3, and so on. So let's go back to our graph and just make sure we don't have overlapping solutions here. 0 is here. That is not overlapping solution. Pi over 3 is here. That would not be an overlapping solution. 2 pi over 3 is here, and so on. So no, we do not have any overlapping solutions, which means the tangent lines at the pole, there are 3 of them. Theta equals pi over 6, theta equals pi over 2, and theta equals 5 pi over 6. Now you could use an alternative version of any one of these. I'll just put subscripts on here. For example, instead of saying theta equals pi over 2, you could say theta equals 3 pi over 2 because that is an equivalent solution. But we have 3 different tangent lines here at the pole. In our next example, we have a polar equation, r equals 5 over 3 minus cosine theta, and we're asked what is the slope of the tangent line to the curve when theta equals 3 pi over 2. The slope of the tangent line is dy dx. So we need to find dy dx. And we know that dy dx equals dy d theta over dx d theta. So we need to get an equation for y in terms of theta and then an equation for x in terms of theta. Y equals r times the sine of theta. Here's my r right here. R equals 5 over 3 minus cosine theta. So y equals that r times the sine of theta. And we'll just stick that in the numerator. And then x equals r times the cosine of theta. So 5 cosine theta over 3 minus cosine theta. Okay, now we can find our derivatives. dy d theta. I'm going to find the derivative of this equation here using the quotient rule. Quotient rule. Derivative of the top, so 5 cosine theta, times the bottom, minus the top, times the derivative of the bottom. The derivative of 3 minus cosine theta is sine theta, so that becomes a sine squared, over bottom squared. Okay, that's my dy d theta. Now dx d theta. So now we're looking at the derivative of our x equation. Again, using quotient rule. So derivative of the top, negative 5 sine theta, times the bottom, minus the top, times the derivative of the bottom, which is sine theta, over bottom squared. We have a fraction divided by a fraction, and these two fractions have the same denominator, so the denominators just end up canceling out. And this simplifies to the numerator of the top fraction, 5 cosine theta times 3 minus cosine theta, minus 5 sine squared theta, over the numerator of the bottom, fraction. Negative 5 sine theta, 3 minus cosine theta, minus 5 cosine theta sine theta. Okay, we want the slope specifically when theta equals 3 pi over 2. So I'm running out of space. I'm just going to come down here. dy dx at theta equals 3 pi over 2. And we're just substituting in 3 pi over 2. The cosine of 3 pi over 2 is 0, though. So this is 0. So this whole term right here is 0. This is 0. This is 0. So this whole term is 0. Okay, so that helps a little bit. The sine of 3 pi over 2 is negative 1. So in my numerator, I have negative 5 times negative 1 squared, which is negative 5. In the denominator, negative 5 times negative 1 is positive 5 times 3 is 15. So my slope is negative 1/3. Slope is negative 1/3. Now, what is the equation of the tangent line at theta equals 3 pi over 2? Well, we know the slope of the tangent line, so that's a good start, but now we need to know the point of tangency in rectangular or Cartesian form. So I need to know what does x equal and what does y equal when theta is 3 pi over 2. So let's go back to that x equation and substitute 3 pi over 2 in for theta. We know the cosine of 3 pi over 2 is 0, so the x coordinate is 0 over 3. 0 over 3 is just 0. The y-coordinate will be 5 times negative 1, so negative 5 over 3. And our tangent line equation, y minus the y-coordinate, so y plus 5/3, equals the slope, negative 1/3, times x minus 0, or we can just write x. Now the last part of this question, what angle theta corresponds to the point on the curve with an x-coordinate of negative 1? We have an equation for x. We know that x equals 5 cosine theta over 3 minus cosine theta. So we'll just let x equal negative 1 here. Negative 1 equals 5 cosine theta over 3 minus cosine theta. Multiply both sides by 3 minus cosine theta. It's going to give us cosine theta minus 3 equals 5 cosine theta. Subtract theta on both sides, we get negative 3 equals 4 cosine theta. Cosine theta equals negative 3/4. Now that's not one of our special ratios, so I think the best we can do here is to say that theta equals arc cosine or cosine inverse, because I don't have enough room to write arc cosine. Cosine inverse of negative 3/4. And for our final problem here, we are looking at two different polar curves, r equals 4 and r equals 4 minus 3 sine 2 theta. And we're only working on the interval from 0 to pi, so just quadrants 1 and 2. Let's keep that in mind. For r equals 4 minus 3 sine 2 theta, we're asked to find dx d theta when theta equals pi over 3. So we need to write an equation for x, and we know that x equals r times cosine theta. And here's our r, so 4 minus 3 sine 2 theta times cosine theta. And now to find dx d theta, we just take the derivative of this equation with respect to theta. So I'm going to use the product rule, and dx d theta equals, so we'll take the derivative of the first factor. Its derivative of sine stuff is cosine of stuff times the derivative of the stuff times the negative 3 that's already there. So negative 6 cosine 2 theta. Okay, so that's derivative of the first factor times the second factor plus the first factor times the derivative of the second. And the derivative of the second is negative sine theta. So let me fix my sign. Oh, not that sign. That sign. change that to a minus. Okay, now we just have to substitute pi over 3 in for theta. Let me come up here. So dx d theta at theta equals pi over 3. I wrote that funny. Say at theta equals pi over 3. There we go. Equals -6 times the cosine of 2 pi over 3. The cosine of 2 pi over 3 is -1/2 times the cosine of pi over 3. The cosine of pi over 3 is 1/2. Okay, minus 4 minus 3 sine 2 theta. So this one's not going to be as nice. 4 minus 3, the sine of 2 pi over 3 is √3 over 2. √3 over 2. Okay, times the sine of pi over 3, which is also √3 over 2. And then simplifying this, I'm going to have 3/2, it looks like. Let me check that again. So that's the negative times negative is positive, and then we have 6 over 4, which is 3 over 2. Okay, 3 over 2. Now I need to distribute this square root of 3 over 2. So minus 2√3, and then minus √3 times √3 is 3, times 3 is 9 over 4. So 3 over 2 is the same as 6 over 4. 6 over 4 minus 9 over 4. Oh wait, I wasn't careful about my signs there. This one was a double negative. So I'm actually adding 3 over 2 and 9 over 4. So 6 over 4 and 9 over 4 is 15 over 4 minus 2√3 as our final answer there. That is the value of dy or dx d theta when theta equals pi over 3. And for the last part of the problem, the distance between the curves changes when theta is between 0 and pi over 2. Write an expression for the distance d between the curves for theta between 0 and pi over 2. So just quadrant 1. Let's refer to the graph so we understand what we're talking about here. We just have to graph quadrant 1 because theta goes from 0 to pi over 2. So in quadrant 1, we've got the equation r equals 4. We know that's just a circle centered at the origin. Okay, so that will be like that. 4, 4. Here's our origin, 0. And our second equation here, r equals 4 minus 3 sine 2 theta. I'm just going to go to the calculator to see what that graph looks like. That's not one that I recognize. Okay, that's looking kind of like something like that. And we're asked to write an expression for the distance between the two curves. So let's just say, for example, theta equals pi over 4. When theta equals pi over 4, we're at this point on the outer curve. So let's name these two curves. We'll call the circle r sub 1, and we'll call this other polar curve r sub 2. So when theta equals pi over 4, here's our point on r2, and here's our point on r1. The distance between the two curves would just be the distance between those 2 points. So it's going to be the r value for the outermost curve, the r1, minus the r value here for this inner curve, and that's the r2. So the distance between the points is just the r2 minus the r1. If we think about an angle of, let's say, pi over 6, same thing. We've got this point on the outer curve, this point on the inner curve, and to get the distance between them, we just want to find what is the r value when theta equals pi over 6 on that outer curve, which is r1, oh, I mixed up my subscripts, right? R1 is the outer curve. So let's fix that. It's R1 minus R2. Right, R1 is the outer curve, and then we want to subtract the R value going to the inner curve. And that difference is going to give us the distance between the 2 points. So our distance equation is just R1 minus R2. 4 minus 3 sine 2 theta, and that simplifies. This becomes 4 minus 4 is 0, and then minus minus 3 sine 2 theta. So that's the equation for D. The second part of the question says find the rate at which that distance is changing with respect to theta. So we're asked to find d theta when theta equals pi over 6. When theta equals pi over 6. So now we simply have to find the derivative of our capital D equation with respect to theta. So d prime, or d theta, equals derivative of sine of stuff is cosine of stuff times the derivative of the stuff times the constant multiple that was already there. So 6 cosine 2 theta. And then when theta is pi over 6, this becomes 6 times the cosine of 2 pi over 6, which is pi over 3. Cosine of pi over 3 is 1/2. 1/2 times 6 is 3. So the rate at which the distance between the two curves is changing at that moment in time is 3. Our critical thinking question for this lesson: how are the slopes of tangent lines determined in polar coordinates? What does the slope represent? So you want to think about the first part of the question is asking us in polar coordinates. So how would you find the slope of the tangent line in polar coordinates, right? So not an xy equation, but an r theta type of equation. And then what does this slope represent? What does this slope represent? Can we describe this while working in polar form? Do we have to switch back to rectangular form to talk about the slope? Or could we talk about it in either coordinate system? Okay, thanks for tuning in today. In our next lesson, we're going to bring in some more calculus and talk about how you might find the area inside of a polar curve, or even the area between two polar curves. I will see you next time.